Okay, so as usual, thank you very much for coming. And the usual stuff, please interrupt me whenever you want. The online participant, again, please just interrupt me just by opening up your microphone. And also, please let us know that that the thing is just blurry because it is sometimes the case. Okay, so quick recap. Last time we saw in kind of extensive way that how to interpret a very small fragment of first order logic inside a category with finite limits. And I don't want to say anything more about that because we don't need it for some time. But also we had some task, right? The task was to define a topos. And then I said that I need three kind of axioms. And then we saw just the first one that was the existence of all finite limits. And there were the other two, some sort of universal things, right? And so our strategy was that we first start with the category of sets, because the topos should be something set-like, right? And then we pick some structures there, write it in a categorical way, axiomatize it here, and it seems random, but it is not, just believe me. So we did the finite limits thing, and it was just, you have a diagram, the best cone, the greatest cone, by the abuse of language, of course. And so we had that, pullback, terminal, product, I don't know, equalizers, etc. And then with that, now we have, say, if also we have finite colimits, that's also coming. So we have singleton, we have empty set, we have disjoint union, we have product of sets, we have some sort of separation, some subsets, quotients, etc. Right? Then we also saw the second guy. The second one was the exponential object. And also I explained kind of, so the intuition is that it captures the set of all functions from some set to other, right? So, and I also wrote the definition. So it was something like, let's say that I have two objects in a category. At least I have to use it. I have a category and two objects, and by, say, the object C, which is, the interpretation is just P to the A. By exponential, we mean this exponential, we mean C, the object C, together with a map, which is this, right? The pair of C and evaluation map is called the exponentiation if it is the best with this property, meaning that for any other D, such and any other map F, there exists a unique map from D to C, say G, such that this guy is commutative, right? So I also asked you to write at least once or twice the real formal equational thing here, and that's a very good suggestion. So let's do it. So for this guy, really formally, what I mean is this: that C together with a map like this is called the exponentiation, the pair, really, the whole data. When you have this, that for any object D and for any map from D times A to B, there exists a unique map, G, from D to C, such that you have this commutation, meaning that F composition with G times identity of A equals, no, sorry, evaluation composition this guy is f, right? So that's the real formal definition.
Sorry, what is that symbol with the E?
EV, which is the name of the map evaluation.
E.
EV. That's just the abbreviation of the evaluation. So it can be H, any name, right? Sure.
How easy to build a category which has limits and collisions but not differentiation?
I will give an example, of course. Yes, that's a good one. So okay, so that's the formal definition. Again, like all the universal things, you can use that kind of uniqueness and the existence and the factorization, blah, blah, to show that the guy is just unique up to isomorphs. Okay, so we saw this. And so I said kind of that the guy is, the C together, this guy is really the exponentiation in category of sets. And now why? And something else, yes. The three is the axioms of a topos. A category with finite limits, with exponential object for any two objects A and B, with another thing, then the guy is a topos. Right? So this exponential is really exponential in set. It should be, because this is our source of inspiration. So of course, put this guy here. So let's interpret the whole thing in sets, right? This is the set of all functions from A to B. And then we'll say this. And then from B to the A times A, of course, there is evaluation map, right? The evaluation simply reads function f input A, and it just outputs f of A, evaluates it, of course. But the main thing is that it should be the best. And it is, right? Because simply I'm saying that for any f with two variables going from this guy to B, right? You can just simply read your D. So let's say that I have f and define your G like this. Read your D, right? And then you have f, fix your D, and the last one is just the input. Then the guy would be a function from A to B, right? Simply, I'm saying that G of D is a function. G of D is a function from A to B, and it's defined like G of D of A is just f of D and A, right? This is just the usual carrying thing, right? That you have two variables, you pick one, fix one, based on the other, it is a function, right? That could be just a bit complex, but just follow your notes, right? So you want a function here, read D, and you have to compute a function. Let's say that G of D, the name of it is H. So I have to define a function H here, which is a function from A to B, because C is A, all the functions from A to B. So H should be a function from A to B. Now I have to read A and compute something in B. And of course I do FD. So, right?
Is there a, what is the exponential object?
In general or here? Here. Here it is, exponential object technically is just a pair, right? So it is the object. Yes. So here it is just the set of all functions plus this evaluation, obvious evaluation function.
So I apologize for this question, but it's not just an object, it's an object and a model.
Yes.
So when you say object, is that an informal or formal meaning of object?
It is informal, right? So like the product, right? We say that the product of two guys, but it is not really one object. It is one object with two projections.
There's no standard name for something.
As far as I know, they don't use it. Yes. Right. You can say that I have the exponential diagram, Or I have the product diagram, yes, or product cone if it is a cone. So yes. Yes, also. But also then there you need two data. You need the object and yes, but universal object is not just an object. It is object plus the witness of the universality, meaning that you show that your F is home of something. That something is the universal object, and the natural isomorphism between them is also important. So natural isomorphism translated to the morphism. So you can never kill the morphism. So it's always there in different forms, right? So of course, and then this D, of course, it is defined such that after evaluation you get your F, but of course it is unique, right? How else I can define my G? It should be just this. Okay. Uh, okay. So one small thing is that you can write it like this. So that weird guy is, that weird triangle is kind of some isomorphism between two sets. I'm simply saying that okay, so first, I guess I didn't even mention that. Okay, whatever. So if you have a category C, by home, index C of A and B, I mean the class of all maps from A to B. Sometimes people write C of A, B. So with different names. So then what I'm saying is this. So if you have a map from D times A and B, right, from this guy to that guy in C, say, then for any map F here, I'm saying that there is another map G there, right? So, right? Such that, and there is a connection between them. The connection is what? Is that if you have, say, a map here, then you can do this. You can do this. You read your G, say, and then you compute this G times identity composed with evaluation, and you get a map here, right? And then the condition simply says that this connection between F and G is unique, is a bijection, right? So what I'm saying is this. So there is some canonical function here that reads some G and then computes this guy. What is it? Composition of evaluation and G times identity, right? So for any G, I can come up with something like that, right? Whenever I have the evaluation map. There is a natural function from this to this. Whenever you have a map from D to C, you can transform the map from D to C to the map from D times A to C times A, and you have evaluation here. So you can get a map from D times A to B, right? There is a natural way to do that via composition with evaluation. It's a category. So yes, this guy, it is a category, the category that we live in, right? So, but you can just forget it. So that's not really important. So because we are fixing our category now. Let's see. Yes, these are two different notations for the same thing. The set of all maps from A to B, but of course, we're in the category C. Right? Yes, exactly. So what I'm saying is that there is a natural map here, right? There's obvious map here. You read something and you compute this, yeah? Via evaluation and something else. Is it obvious? Kinda. The point is that that condition that I have there simply says that it says that this G is unique for any F here and also exists for any F here, because I'm saying that for any F, there exists G such that f equals to this, right? So this condition, if you write it kind of fancy, then it simply says that this function, this obvious function from this set to that set, is a bijection. For any f, you can find a unique g such that this, right? And this is kind of the things that, so we kind of expect this, right? So because why? Because simply I'm saying that there is a natural map from this, and let's write C as B to the A, right? So this is what we really expect, right? If you have a function from B times A to B with two variables, simply you have a function that you read D and you get a function, based on A. If you have two variables, you can read one and then the other. So they are the same things, right? That is the definition of exponentiation. And it is really exponentiation because one specific case of this is when you put D as 1, right? And therefore, this guy would be all the maps from 1 to some set, and therefore all the elements, right? These are all the functions from A to B. And this side says that it is 1 times A, and it is easy to show that 1 times A is just A. So the guy is home AB, right? So I have some set such that its elements is in one-to-one correspondence with the functions from A to B, and that should be the case, right? Okay. So now I can leave it for a moment, and I want to compute my exponentiation in two other examples that I like. So this guy, and if you remember, this guy was just a category of variable sets. So functions from some A0 to A1 are objects. And if you want a morphism, then it's a pair of two functions such that the guy commutes, right? Sure. No. Yeah, that 2 is the category 2.
Oh, yes.
Yeah. But there is some real exponentiation here that I will explain later. So, right? So you remember this? Objects are just functions and then morphisms. So here, what is the exponentiation? So let's say that I have this A and I have this B, right? These are two objects. And I want the exponentiation. So whatever it is some C, C0, C1, and some function, right? Let's say that's Fg and the guy is H, right? So what is H? Who knows? I can help. But you have to ask for it.
So the exponentiation of what to the what?
These are two objects in this category, right? Yes. So f to the g should be some c plus some evaluation, which is this, say, times what? A. 2, the other one, B. Right?
And that double arrow is the EV function.
The top arrow,
Double arrow.
the double arrow, no, the double arrow is just a map in this category. And yes, so it's just this double arrow. So yeah, okay, if we compute this, we saw that the product in this category is pointwise.
The evaluation.
Yes, yes, that's the evaluation function. But if I want to spell it out, then it means that we check that the product in this category is just pointwise. Therefore, this guy is simply this. H times F, right? And then now I want something like this. Two maps. That's the evaluation. So let's say evaluation 0, evaluation 1, such that you have the commutation and it is the universal one. Wow. Who can guess this? What is C and what is evaluation? Because you have two objects, you have to come up with the explanation, meaning that you need the object, you need the morphism, such that you have the property, right? And that is just a mess, right? So, okay, let's cheat. Maybe it is just pointwise, right? Why not? Everything is pointwise. But it seems that Ondra does not like it, right? Yes, but the point is that of course it is pointwise, but you encode this F and G inside your H, right? Somehow. Like here in the product. You do just pointwise, but then the map inherits the maps. So maybe you can do that. Huh? So what do I mean? I mean something kind of stupid, right? Let's say that, come on, C0 should be all the functions from B0 to A0. C1 should be B1, A1, right? Exactly, that's the problem, right? You can say that, okay, here I have, this is variable sets, right? Here at this point, I have A0, B0, all the functions there, all the functions there, but there is no natural map, simply because what I'm saying is that you have A0, right? And A1 could be kind of bigger. And then you have a function from A0 to B0, but I cannot expand it to A1 to B1 in a natural way, right? So that's hopeless. It's not pointwise. And that is the problematic thing. Or maybe I need this. So how to do that? God. The trick is this. If you are at this point, so we can just play with the arrows, with this mess, and then find something, or think a bit philosophically and sit back, right? So if it is time, then you are at the point 0, right? And you have two sets that vary over time, right? What are the functions between the two? Whatever it is, right? Let's say it is a function, I don't know what's the name, some f, right? That's some entity that we don't know what it is, right? There is a function between variable sets. And whatever it is, there is some f0 and some f1, of course, right? Because the function also can change. The point is that at level 0, if you have a function, then it means that here and also later it works. Of course, because when something changes, it means that we have incomplete information, right? Something is not proved, something is not set, we don't know. Maybe there are two things and later we can understand that they are the same thing. But the point is that if I have a function and I claim that now my function at the 0 level works, it should work regardless of the change, right? So if it works now, if I add more information, find some equality, new equality, add some new things, it must preserve the structure, right? Because otherwise I need a function that operates over incomplete data, kind of. Okay, that's kind of very weird. So if you know intuitionistic implication, that is just the intuitionistic implication, right? So then what is it? C0 is the set of all maps from, okay, no, that could be confusing. Sorry. It is the set of all morphisms from F to G. So if you like home FG, meaning that when I say I have a function from A to B, I mean at the zero level, I have A0, I have A1, I have B0, B1, and any pair is a map, right, between them. Pick all the pairs and store them in C0. Simply, I'm saying that at the zero level, if I have a function, it works here, and also it works there. So I have the whole information. Okay.
Sorry, in general, you're saying that in this particular category,
Yes.
you can interpret the exponentiation this way, or this is the unique thing?
It is unique up to isomorphism, but this is just my construction of it, or the proof that it exists, if you like.
So you're proving that in this category, exponentiation does good.
Exactly. And this is my construction.
And again, unique up to isomorphism means that if, well, there's something about drawing diagrams, but I don't remember.
Yes. So here unique up to isomorphism means this. Maybe that's the right. Okay, so let's say that you have two exponentiation. So first you have C1 evaluation 1 and C2 evaluation 2, right? So then you have this. You have C times A, 2, B, C1 evaluation 1. Also you have this C2A evaluation 2. So what I mean is that there exists, I mean more, but for now, what I mean is there exists some isomorphism between C and D, let's say it's from C to C1 to C2, such that, let's say the name is F, right? Such that F identity A makes this commutative.
Okay, I guess that turns up somehow from the maximality or something.
Exactly, exactly.
And what conclusion should one draw from this picture?
At first, if you have such a pair, these two guys are isomorphic really as objects. And even more, the isomorphism maps one EV1 to EV2, right?
So particularly in any bigger diagram, swap, you can replace C on this.
Exactly, exactly. So, okay, so that weird guy is just my C0, and my C1 is all the functions from A1 to B1. So let's say this. So this home is in set, this home is in set 2, right? Because it is just one, it's just maximum, right? Ah, thanks. It is the maximum, and so there is nothing more than that, right? And what is the map? Of course, when I have two maps here, you can just forget this, and then I have that. Right? What I'm doing is just the point-wise thing, but here I'm restricting myself to not just all functions from A0 to B0, but kind of all the functions that is preserved on the time or on the variation. So therefore, I have just a pair. And you can check that it is just the exponentiation. And what is the evaluation? I won't say. Should I say it? Sorry, yes. So it is, it's my bad. So it is really. So the home, that's not good. Okay, so the home in set squared, come on, let's just, Ah, that's just too good to be true. Okay. Yes. Thanks. So the home is in set to the 2 in the main category that we have from our 2 objects, F and G, right? And this guy here, I wrote home in set between A1 and B1. Okay. And then the function is obvious one. And
Where are zero?
they are sets.
Are they part of F and G?
Yes.
So F and G doesn't mean morphism there, it means
The objects in this category. Or functions or morphisms in the category set.
I think I don't understand the basic thing. So the category set.
Yes.
Objects are these 3 things, A0, A1 now.
Yes.
Which sometimes you're calling it F.
Yes. Okay. So I assume always that when I write a function, it is clear from the definition of the function what is the domain and what is the codomain.
Okay.
So it is the part of the definition.
In this case,
Okay.
so one meaning is, well, actually,
Yes,
but maybe
that's
one
true.
meaning is one meaning is the whole.
Exactly. It depends on the category. When you are in set, it is just morphism. But then set to the 2 is defined such that all the morphisms actually there now are objects in the new category, and the morphisms are something else.
So your object C0,
Yes.
so C0 looks like it should be some sort of A0 thing, but it's not.
Yes. So the canonical thing is that all the functions from say A0 to B0, but the problem is that if I have all the functions from A0 to B0, they are just too much. So I don't know how to expand the function.
But the reason you're allowed to mess around like this
Uh-huh.
is you have that it's unique up to isomorphism. So whatever strange object you choose,
Okay.
it will be somehow the right object.
Yes, but the point, okay, the point is that I'm not, okay, it seems crazy, but the point is that, who cares? The point is that there is one definition, and that's a natural definition, right? It is there. Depending on the category, you may need to work with crazy objects to show that the guy exists. But then, since it is unique up to isomorphism, after the existence, simply we don't care, except in the cases that we have to really do computation, right? Let's say that some guy says that there is, in this category, the exponential object has this property, and it is not something general, so you have to do the computation.
In this case, could you done it the other way around? Like set C1 to be this F and G, and set C0 to be A0.
No. The order matters. So. Okay. So, okay, yes, that's crazy, but it is not really. So, what is my second category? Sets, the category of G sets that I wrote like this, right?
Sorry, so you finished with it?
Yes, yes.
So what is the theory?
What do you mean?
The exponential in itself.
It's, I don't get it. So I have a category which is not a category of sets, right? So then I have some object and I described it set theoretically, right? Meaning that here I have 2 sets. The first set is just a set of all pairs of functions such that you have the commutativity. Here you have all the functions really from A1 to B1, and you need a function, and the function is just the projection function that reads 2 maps and just provides the other. So, but I guess it is not what you mean.
No, I meant that the exponential in sets is the set of all functions.
Yes.
So what is exponential in set 2?
It is again the set of all functions, but functions are here the morphisms in the new category, or the functions that respect the variation of time. And so it seems kind of weird, but it is really capturing the idea that if you have a function, say, from a varying set to another varying set, of course you have two functions, right? That one is from the 0, from the 1, such that it respects the variation of time. And whenever you have a function, it must respect the growth of time. So if I have a function now, it also works later, right? So that is the idea that here I have all the functions, and then you forget. I know it's not natural, but
There's a of physics that defines that this is the set of all.
yes,
So can you say that this is the set of all functional functions?
I kind of did. I know. The point is that I need two sets, and it makes everything harder, right? But if you allow me just to define anything set theoretically, but based on one of guys, so this is just all the functions from A1 to B1. That's good, right? And this is all the morphisms from the whole thing to the whole thing. So is it good now or not?
But we know what a morphism means. But what is a morphism again in this?
Pair of two maps such that you get commutativity here.
So what if, is there some concrete example for A and B and so on?
Of course. So
For
you.
example, I guess is if A0, B0, 1.
Uh-huh.
Then what is it?
A0, B0, these are 1. So then what happens to the other two? They are also important. Okay, so let's compute them. Let's say that A0 and B0, if it helps, they are both singletons, right? Just ones. And I don't care about the other two, right? Therefore, these two guys are simply what? They are 2 points, one here, one there, right? Because they are just maps from 1 to these guys. So I have 2 points. So Neil says that, okay, if this is my A and this is my B, then what is C0? So C0 is just a pair of all two functions such that you have this. So this function is unique. It is just from singleton to singleton. Who cares? So simply, I'm saying that because your F and your G are fixing two elements, let's say A and B here, right? So then simply you are saying that your C0 is just a set of all maps from A1 to B1 such that F of A is B, and your C1 is all the functions. And your map is just inclusion. Is it good enough? Yes. Sure. What's inclusion here? And exactly this is why category theory is good. Because it gives you the universal things rather than the explicit constructions, because the explicit constructions are usually just weird.
So at what point do you run into foundational issues about whether these new objects exist or not?
I never do, but
You're happily writing out some new
yeah.
things by
Yes. So there are some foundational cares that I don't care, but so here, for instance, you don't have any kind of foundational care because usually my category of sets, everything is inherited from there, and my category of sets say it is a model of Zermelo-Frankel, CFC even, right?
So particularly you know that these common things are existing sets.
Yes, because so I'm describing the thing, right? It is just a set of all pairs of maps of functions between fixed things.
Yes, but start, you said they could be class functions or something. Okay, I don't remember.
Yeah, the whole category could be, but these are just concrete things at least, right? So also there it is important that sometimes your C should be small, everything should be a set-like thing, sometimes it should be finite, whatever. But this is just valid in set theory, right? Okay, so my set to the G, okay, is this. So if you have the category of G sets, G action, whatever the name is, so you have, say, two sets with two actions, right? So you have the category set G, meaning that if you have two objects, you have just two, say, sets with two actions from G, right? And if you don't remember, you have to remember that this guy is just a function from x times G to x, such that identity maps everything to itself. And if you compose here, then you compose the functions, right? So if you have these two, then what is the exponentiation? It is even more weird. So the exponentiation is this. The set of, okay, so I have to mention first that you remember what is a morphism here, right? So a morphism is some function from x to y such that it respects this guy. It respects the action, meaning this, right? So now I have two actions. What is the exponentiation? The exponentiation should be a set with an action, also with some evaluation function, right? So naturally, you guess something like all the equivariant functions or so, right? Because these are the morphisms. But the bad thing is that no, it is actually all the functions. But then the data stored here in, okay, so let's say Z, this is what I want. My Z is just a set of all functions. And then if I have a function f times the element G, so let me write this. If I have function f from x to y times G, it is simply, so applying on x, it means, I guess, apply f on x times x G minus 1 times y G, if I'm not mistaken. So that's the weird thing, right? Again, I don't care. You have to go and check all the details, but the point is that this is a good category and you want the exponential object, and this is your exponential object. But also it gives your justification, right? So because if I were new to the thing, then I would say that okay, that's the natural set to consider, all the maps that preserve the thing, and then some action maybe. But then usually in mathematics, you get it from the experience at some point that no, this is a good guy, that you have to work with this. Category theory just gives you the justification that this is good simply because it is exponentiation. That one is somehow natural, but it's not good because it's not universal, right? So it looks internal. That if you interpret everything internally, if you forget for a moment that these are sets with some actions or whatever, if they are just some things and you know morphisms between them, what would be the natural exponentiation object that you have to consider? And then that's it.
I'm not sure I can read what, but so you had the sets x and y.
Yes.
With the actions by G.
By fixed G, yes.
You find Z to be y P x Functions morphing.
Yes, all of them. And I have to define the action, right? So f is a function from x to y in z. Yes, f is an element in z.
Active on right
Yes, and it should be something also in z.
should give you. Okay, so if I give you element Z, and it takes something from Y, so back at X, you. What's
Okay.
that? I can't read that letter.
Which one?
It's X.
This x. So you have your x, you apply g minus 1 to x, compute f, and apply g. But this time in y, first time in x. Right? Of course.
It may be incorrect. So imagine if I'm in this category structure set,
Mhm.
spaces of groups up.
Yes.
And my goal is to check whether there are exponential objects or not. So for example, for vector spaces, I would just literally consider the set of all morphisms, and if it has natural structure of vector spaces, then yeah, it will be a specification. But for groups, this set of morphisms will probably does not have structure of group.
Mhm.
Expect expectation objects exist in groups, two exist in groups.
Yes.
So it is.
Yes and no. So it depends because this whatever you consider is kind of subjective, right? So as I said, so here you may say that okay, that's the natural thing to consider, but it is not. But sometimes, usually, you go for natural thing, or at least to find something that's forced upon you by the definition, and you see that if it works or not. And sometimes it doesn't work. Okay, so what is evaluation? Evaluation is just evaluation. First, I have to say that, meaning that from z times x. So if I have z dot z times x times y. So I need some evaluation and should be a covariant map. And we saw that this guy is just pointwise. So then simply evaluation reads f and x and just evaluate it as in set. Why it is equivariant? Because of this definition. This is defined to make it equivariant. Right? Equivariant means that you respect the action. And you respect the action simply because if you apply it, on gx, then you cancel out g by g minus. That's just a game, right? Okay. So now I promised to find an example of something that has no exponentiation, but
This is how difficult it is, how to prove that these are exponentiation.
not really.
Not going to definition.
Yes, you have to open up everything and check everything.
So in particular for this minimality, obviously maximality
Mhm.
condition, it's just you can do it.
Yes. So when you work with something set-like, usually that map from, because what you have to find really is the map from D to C. And that guy is just the usual carrying map in set with the natural structure such that it makes everything, Sure.
I started with the wrong natural object
Mhm.
and tried to check the exponential conditions for it.
Mhm.
Would that give me the idea of what I'm missing to actually solve it?
I guess so. I guess so. So if you write it down okay, I guess so. But usually you see that, you are missing something. It is just too small. It's just too big. It collapses the action, something of that sort. But this is specifically, I guess you can see it really if you write it down. But I cannot be sure, right? I have to write it down really to see.
It's related to that. Is there a category for which it is unknown if it has an exponential object?
Yeah, yes,
Yes.
yes. Now I want to give an example.
Please.
Yes. So, of course,
These both examples are of the form set to something.
set to something.
Is it true that every something being a finite category gives you exponential?
Yes. So you have to know the basic definitions there, and I won't do that. But we will see that. So the question is that so the categories that we have are set to something, but for us this is just a notation, but it has a meaning, right? That when I write set to G, when I write set to 2 or set to 1 is just a set. And then I say that these guys all have the exponentiation. Then the question is that, is it true that for any set, say set to C, for some category C, whatever it means, we don't know now, does it have the exponentiation? The answer is yes. So, of course, one of the important foundational issues is that this C should be small here. But for now, I don't care. So, okay, I promised to give you some categories without exponentiation. Technically, it is just something rare. So maybe you can find many categories with limit, co-limit, right? But exponentiation is a bit, for me, maybe even more than a bit rare. So it's not like that always you have function space. And that's a very, very, very annoying thing. Simply because you want your function space to work with in some settings, and there is none. And that's bad. So to give you millions of examples, I start with one, and then you see how to prove the non-existence for family. So let's say that I have the category of all groups, right? And homomorphisms, of course. Here you cannot have the exponentiation. Of course, some groups, some groups exist, right? Some exponentiation exists, but not all of them. How do I know that? By this trick. So let's say that it exists for any group G and H, right? Then it means that I have an object, say H to the G, such that from 1, you get this, right? We saw this, right? All the elements, but element means map from 1 to this. So what is 1 here in the category of groups? What's the terminal? It's the trivial group, right? Yes. But at the same time, it is also initial. So this group, E, say, right? This is both initial and terminal, right? Initial because there's just one map, homomorphism from this to any group. You have to map E to E. And then it is terminal because it is just single. So there is just one function there. And also it is homomorphism, right? So, okay. But then it is initial. Since it is initial, it is also 0, right? Because just the game with the notation. And from initial to anything, you have just one map. So this guy is just one map. So if I have just two groups with more than one morphism between them, then it can, so the exponentiation cannot exist, right? And this holds, of course, for all the categories where 0 is isomorphic to 1. Terminal and initial are the same things. Yes, terminal. Terminal, 1 is called terminal when there exists exactly one morphism from anything to 1. And the dual one is, it is initial when there exists exactly one morphism from the guy to any x. So instead, for instance, this is empty, because there is one function from empty to anything. And this is a singleton, because there's a one function from anything to singleton.
If you draw a diagram, 0 arrow to x with an arrow to 1,
Uh-huh.
that's not saying that 1 is the same as x, because it doesn't commute backwards or something.
Yeah,
It's not a.
there is, of course, there is one map. That's a good one. There is one map from 0 to 1 from both sides, right? So we know that there is a map here, and the map is unique, of course, but it doesn't mean that it is an isomorphism.
I'm just saying, even in the case when 0 and 1 are the same,
Yeah.
have a map from 0 to x and back to 0,
Okay. So
right?
yes.
But it's not saying that x is isomorphic to 0.
No.
Because it doesn't commute to one way or
It doesn't commute. Okay. The composition is not identity.
well, one of the compositions is.
Yes, but not the other. Right?
So sorry, that's 0 and 1, and you're saying,
So now I want to compute in G the category of groups, the 0 and 1, both are this guy. Do you accept that, right? Okay. So then I'm saying that whenever you have this in a category, right, that then it's called the 0 object. And that's usual in all kinds of algebraic categories. So all the category of groups, abelian groups, vector spaces, as you said, I don't know, modules for some fixed R, you know.
Even though in vector spaces, like
Yes.
you don't have special object, even though like in vector spaces, if I take the set of morphisms.
Exactly.
It is vector space, like natural one.
Of course.
It's not have
No. Yes. So that's kind of crazy, right? So, but it's not. And in none of them, you have the exponential simply because 0 is 1. So I can do the same game, right? So I can write home 1 to exponentiation. So you have this, 1 is 0, this guy is a singleton. So then home should be singleton, right? And in none of these categories, home is always singleton. And you can say something more general. If 0 is 1 in category, and it's not a pre-order, you have at least objects with more than one morphism, then you cannot have your exponentiation. So that's one way to kill all the algebraic examples. But even worse happened. This guy also does not have exponentiation. The category of all topological spaces are continuous maps. That is really annoying. Because come on, so you work with all the continuous functions from x to y, as you may suggest, right? And then there is some sort of topology, compact open, whatever topology, and then it should be, but it is not.
The set of all continuous functions, there are multiple natural.
Oh, yes, of course. Of course.
None of them works.
None of them works. Always, of course. Sometimes it works, and we have the characterization that if you have some fixed x, then y to the x exists for some x with some sort of compact blah blah that I don't remember, but there is a characterization, and it is really annoying because come on, so you have all the so let's say that this is 0, 1, you have all the paths from in x, which is all the maps, all the continuous maps from 0, 1 to x. You want to store them in one space, but you cannot. You can actually because it is 0, 1, but usually you cannot, right? And that's bad. So people try to solve this problem simply by doing two different things. Sometimes shrink topological spaces to some spaces that we care about, some CW complexes, blah, blah, the usual thing, or compactly generated or compact store or whatever, and then you get your exponentiation. Sometimes you have to expand it to bigger so-called spaces where you have really exponentiation. And it is kind of handy in the homotopy theory, for instance, to have the function space really. It's not that easy. Yes, it's not that easy, so I cannot just explain. So, okay, these are the things, and now I have to say. Maybe there is, but I'm not aware of. Yes, maybe it is the yeah. There is something in groups, but I don't know. I've never seen something of that sort, but
Or in general, like
or maybe even it is easy, right? So I don't know.
like sometimes exponentiation fails, but
Yes.
other cases when it fails, but know exactly which pairs are exponential. Like this one in topological cases, like there are x's for which every one
True.
works.
True.
But if you wanted to characterize all the pairs, is this sometimes done?
I guess in groups, for instance, maybe it's not that hard, right? So you want your G and H and you want your exponentiation. At least we know that the home of GH should not be non-subsingleton. So it should not have two objects, right? But then so you can think when it has more than two objects, it should not be that hard to find it out. Maybe, your H is, if you have just a bit of G and H, you get more than one morphism, I guess, no? But anyway, so you can just play with this and then find all of them. So I guess then maybe it is kind of easy to see that yes, it should be. Okay. Huh? I don't know, but you have to play with this to see. So then what? Then we saw the Heyting algebras, right? We also had the example of Heyting algebras that I remind you, and then I come back to that. So what is, let's say that you have a poset, right? And then what is the exponential object in a poset? So you have A, B. Of course, your poset should have the finite limits, because otherwise how to write A times something, right? So then I have two objects. What is the exponentiation? It is C together with the map, with the evaluation, but the evaluation map simply is just saying that the guy is less than this, such that for any D, if D is less than this, then D is less than C. And I said also that people write this for the Heyting implication, and then these two data transform to simply that D times A is less than B if D is less than A. So you can see that home thing that we had before, right? It is isomorphic to home D times A and B, right? So we had this. And home simply means that this is because there is at most one thing here. So it means that D is just less than A implies B, if and only if that D and A is less than B. So this is just the propositional version of that. So, and then we also saw one example, one canonical example is that if you have a topological spaces, the opens with inclusion is a poset where you have all the exponentials, meaning that if you have two opens, then U implies V simply is U complement union V, but the interior of it, right? So you have to, of course, check. Again, it doesn't matter, right? It is unique. So this is my definition of it, right? But so then, so that's easy to see that this is also the Heyting implication, but in power set of X, right? It is just the usual implication that we have in logic, right? And when you restrict yourself to opens, you have to get the interior to make it open, right? Then what? Besides this guy, I guess I have time to dare to go to the last one. Yes, the objects are the opens here. You mean here, right? The opens of the topology. Yes, with the inclusion, and it's a poset, and any poset is a category. So in that sense. So, okay. Finally, what is the last one in the definition of a topos? Yes, of course.
So we will show this example where it's like unknown, where the category has or doesn't have potential, where it's like conjecture, open problem.
I don't know. I really don't know. Maybe there are some, but it should be some crazy category that's really hard to prove that. Even for topological spaces, it's not that easy. So I guess there should be some. Okay, so any question for exponentiation? No. So now I have to move to the last axiom. And what is the structure that I want to use? And then make it categorical and use an axiom as the last axiom for toposes. So, so far, this is just huge structure, right? You have all finite limits and you have exponentiation, right? But it's not like that. It's just too much, right? So you can find this kind of everywhere, right? Not in topological spaces, but you can change a bit and you find the structure. Finite limit and exponentiation is not that rare compared to what I want to say. And this is the real power in a topos, right? And it is far easier. So the guy is this. So I have to have something in sets and then bring it out, make it categorical. What I have is what? Exactly. Exactly. So we have the set of 0 and 1. But of course, it doesn't say anything. So what? So in any category, you can have something at 1 plus 1. If you have finite limit, co-limit is kind of 0 and 1. No, what is the role of 0, 1? So you have this subset. You have 0, 1. You have 1 as its subsets. It's subset, right? And this guy is a very, very good subset. In the following sense, that if you have any other subset, say y as a subset of any x, any y, any x as a subset, then you can find the characteristic function of the subset. You can write a map from x to 0, 1 that evaluates something in x to see that whether it is in y or not. If it is in y, it maps it to 1, otherwise to 0, right? We always have this. Any relation has the characteristic function. This is the set theoretic thing that we have. This is a very important thing because you map substructures to functions, right? Relation function connection. And it seems it's not that important, but it's really powerful. So, okay, how to make that intuition that you have characteristic function of any subset into a categorical diagram. And I wrote kind of almost all of it. So you have to say that, of course, there is one map here because it is just 1. There is 1. This guy is commutative. Commutativity simply says that if you start with something in y and go here, you get 1. And so y are the characteristic function, also you get 1. Simply it says that the characteristic function maps y to 1. But it does not say that it maps nothing else to 1. For that, you need your y to be the biggest one, meaning that this guy is a pullback, right? In other terms, maybe it is good to say that if you have a characteristic function of y inside x, let's say, so then being a characteristic function simply means that the inverse image of 1, right, is exactly y, right? Just y goes to 1 and nothing else. So to say that inverse image is a pullback, right? Inverse image of something is a pullback of that something, right? And then it is y. Okay, so I can make it fully categorical, like this. So you say that you need some fixed object. Let's call it omega. 1 map from 1 to the omega, let's call it t, such that for any sub-object, meaning that for any monic, there exists a unique map, because of course characteristic function is unique. It's determined based on the subset. There is a unique map such that this guy is a pullback. Right? So this is the twice thing that I can write it in a formal way. So say omega together with a map T from 1 to omega. This pair is what I want, and it's called sub-object classifier for obvious reasons, because it classifies all sub-objects. Sub-object classifier simply is object map from 1 to the object, such that for any object X and Y inside the objects of the category, and for any map M from Y to X, if M is unique, that you know what it means, then there exists a unique map, say F from X to omega, such that this guy is a pullback, meaning that T composition with this equals to F O M, and something else to say that it is a pullback. That could be just big. Yeah? I simply say the obvious thing, right? So you have just, no? Is it good enough?
Sorry, what's the, you said all X, Y in some,
Objects, sorry, my bad. That's just worse. Okay. So I'm simply saying that I have something and some element of it acting as 0, 1, and 1, and any other monic is, just corresponds to one characteristic function. So what's the interpretation of this omega? What is the interpretation of 0, 1? So when we say that we go from X to 0, 1 to classify being in a subset or not being in a subset, so you are saying simply that the elements in this set are values. You're two valued, right? Something is or is not. So this omega then is your object of values in your category, right? It can be more than binary, so you can many values somehow. This guy is just a truth value, 1. So this map then is the truth value. So you have the set of values, the object of values, and the truth value. So some values, you pick one to say that this guy is my truth value. So equality to that means it's true. And then you are saying that your truth value is powerful enough to capture all the monics, in the sense that you can find valuation for the elements in X, such that if something in Y, it gets 1, and it gets 1 exactly when it is in Y, and on something else, it gets something else that we don't know. It says nothing about that, right? So you have some notion of valuation. Okay?
Should we only assume which explicitly speaks of monics?
Yes.
But would it make sense to consider only some special class of monics and
Sometimes it is.
embedded?
Sometimes it makes sense, but of course not in Topos theory in this way. Yes, and even more, so we have classifiers, right? So this is sub-object classifier. You can have different classifiers. One point that I have to mention is that you may say that, okay, why just monics, right? So the point is that this map is always monic. Any map from 1 to some z is monic, of course, because monic means that if you have 2 maps, you cannot have 2 maps, right? To 1. So from 1, everything is monic. Pullback of a monic is monic. So of course I have to start with many. So I cannot generalize it in exact same way, right? But if you change the one, then you can do something. Okay, so universal. Okay, where is the universality really? Because I promised that everything that I want to present is universality, right? Yes, it is pullback in some sense. There is universality, but there is more universality than that. Who knows? There is some formal definition of universality that I didn't say anything about, but my reading now is that it means it is the best solution to something, like the limits, like the exponentiation, in a very informal way. And then here it is, something is the best in something. And the best thing is this guy. So it feels weird, but really it is the best sub-object ever. It's a best sub-object, meaning that it's a sub-object because it's monic, as I said before, right? And any other sub-object is the pullback or inverse image of it, right? So this is the best, the generic sub-object, generic subset. You have it, and if you want something else, just inverse image, right? This is the greatest possible ever sub-object. And in some sense, it makes sense because the whole information of being a subset is just here, right? One is in 0, 1 and nothing, and 0 is not. So the whole valuation means this exactly, right? For subsets at least. Okay, so I have time to play with this guy and provide some examples. Called?
First one was
The existence of finite limits, the existence of exponential objects, the existence of sub-object classifier. Yeah, this guy is a sub-object classifier. So this is the definition of sub-object classifier, and the third axiom is the existence of this. And initial terminal is in the finite limit thing that we had in the first axiom. In the first formalization that Lavier came up with, he had really finite colimits as also one axiom. Later on, it was proved that based on these three, you can prove actually that you have finite colimits always. So there is no need for that. So it's kind of implicit there.
The universe is not empty.
That's a very good one. Of course, universe is not empty because I have finite limits. At least I have terminal. But the bad news is this. This guy is a topos. One object, identity over it. This is the degenerate thing that you care, right? So this is also topos. That is the worst topos ever, right? So it's just very small, but it has a purpose really. So the purpose is that let's say that in ring theory, you have many rings, and one of the rings is just the 0 ring when 0 equals to 1, right? So people use that ring as some sort of contradiction, right? That something is collapsing. So you can do exactly the same thing with some theory that's called classifying topos. So if you have a theory, always you can construct a topos from a theory such that it is just the best topos ever for the theory, meaning that it's a universe. In the universe, there is one generic model of the theory, and it is the best, meaning that for any other topos, for any other model, you can factor it through this. This is a generic model, right? And then sometimes that topos is 1 when the theory is inconsistent, right? So yes, there is some very bad case, and that is the only bad case. And we also saw many examples. Actually, we are going to see some. But of course, for now, 1 and set, those are toposes, right, in this definition. And so I need to explain at least maybe one of the examples. So let's say that we are again in this crazy category of variable sets. And since everything is variable, maybe you have the hope that something non-trivial happens to the values, right? So what is omega? Omega, whatever it is, it should be two sets, one morphism, right? So what are these two sets? Help. It should classify being a subset, right? Being a subset means that you have two sets, two subsets, right? And how many values can happen? So you have two sets, say x0, x1, y0, y1, right?
The existence of sublottery classifier.
Yes.
The axiom says there is some omega. It's not that for every omega you have this property. It's there's some particular.
Yes, yes. There exists one omega, one map from 1 to omega such that it is the opposite. Like the product or the exponential. It does not say that everything is exponential or everything is product. So it says
You have three special objects in your
more than that.
Zero.
Yes, yes, at least. And sometimes they collapse all to one thing. But okay, so like you want the valuations, right? So valuations correspond somehow to being a subset. So being a subset means that you have two subsets here. You have to work it out, but a monique means just two subsets, say, with the same map. And then how many values capture really being in a subset here? So here, for instance, you need two values. Either the guy is or is not. So then I would say that this is 0, 1. And what about this? Here, there are more than two. The element here either is in y0. So you have some element in x0. It is either in y0 or it is not in y0, but it is in y1 when you go up. Or when you go up also, it's not in y1, right? So it's like that you have something, it is in your, it has the property. It has the property y. Or it does not have it, but later it has it. Or it never has it. You have three values. 0, 1, I would say unknown. And unknown goes to 1, the map. 0 to 0, 1 to 1, I need a map. 0 to 0, 1 to 1, unknown to 1. Because unknown is the one that becomes 1 later, right? It is simply just a Kripke model, the intuitionistic semantics, if you know it, right? So this guy is a subobject classifier, simply because of this argument that I gave you. It's not really. So it is some sort of Heyting algebra. So, and then, of course, I need one map from 1, which is star star identity, to omega, and this would be my t. So let's say t1, t0, and then 0, 1, 0, 1, yo. And of course, I pick 1, 1, right? That is my true, always true. So if you think, because I promised something about independence, right? So if you think about forcing, it is like that you have, so this means that it forces to false. This means it forces to true. This means that it is incomplete data. You have to wait to make it forced, right? Okay, so then this is my omega here. Maybe it's also good to see the omega here. So the omega here is just easier. So it is simply, it should be one set, one, action. So the set is 0, 1, and the action is trivial. The action is like 0 action G is 0, 1 action G is 1. So it does not change anything. It's kind of weird because you expect something more, right? But again, like the exponential, which is weird in this case, it is encoded somewhere else in the classifying map, not here. There, it was encoded in the action over the function space. So it's something like that happens. So you can see that. And so therefore, these guys are all toposes, as I promised, right? And I want to also add one topos that's not kind of between them. And that one topos is the category of, so just find very obvious category with all the properties. What? Toposes. That was a good one, but no. No, that's just big. Very something set like. So. Not all sets, but finite sets, exactly. So finite sets. Because of course, in finite sets, you have all the finite limits, because it's just finite limits. You have exponentiation, the functions of all sets to finite sets, finite exponential. 0, 1 is also a finite set. So it is not one of them, but it's also a topos. Okay, so the closing thing for 1 minute, 2 minutes is some philosophical nonsense. So what I want to say is actually to draw a picture to provide some intuition that what are really toposes. We said that they are kind of set-like words, and that's true. But I guess it is better if I write this down. So we saw this diagram. No, we didn't. But now we see it. So here we had Heyting algebra, right? What is a Heyting algebra? It is a Cartesian closed category, which is also a poset, right? So you have all finite limits. You have the two axioms, all finite limits, all exponentiations, but we're just over a poset, right? I have what? No. Yes, I have joins. That's right. I have also finite colimits. That's true. Sorry. Yes, I have. And then we saw some examples, right? For any topological space, this guy is a Heyting algebra, right? There is another one, and if you know logic, then the set of propositions, say all law intuitionism, and probability. It is also Heyting algebra, right? So my objects are just propositions. Propositions mean just formulas, say, with conjunction, disjunction, implication, and but it is constructive, meaning that you don't have any proof by excluded middle, say. And then this order that you need, and also you have here, right, is just the order of probability. Okay. So this connection is kind of tight in some sense. So yes, it is an example, but you can make everything, some sort of proposition-like, if you like. So the algebra and logic are kind of close to each other. So this is pure algebra, this is logic. And here you have topology. So algebra, logic, and here you have topology. And this connection is loose, so really something is between. Something is there that is just complete Heyting algebras. So a complete Heyting algebra is just a Heyting algebra when you have all the limits, say, right? There's something in between, and then these two are kind of close to each other. But the difference is, because it's kind of algebraic, this is topologic, the difference is between morphisms. So if you preserve every Heyting structure, like implication, etc., it is more algebraic. if you preserve infinite join and meet, then you are topologic. You are preserving opens, right? So it depends. So
Those were properties of two different maps, or
yes. So these guys come with maps, some structure preserving maps. Depending on what is the structure, there are different families of maps. So one is more topologic, one is more logical algebraic, right? So my point is that this is the reason that there is some sort of connection between topology and logic and also algebra, and we all know that, right? That you can interpret intuitionistic logic via topological spaces or find the common ground for both of them as the Heyting algebra. So my point is this. So what if I generalize these two? So the generalization of this would be, again, just propositions, but not just the order, because order means that something is less than the other. It proves that. Let's say that I also care about proofs. So there is more than one morphism between any two objects. Not just provability, there are different proofs, and I care about the structure of proofs, right? So let's say that explicit proofs. So I'm going simply from what? From poset to category, right? So here you have to go to a category. The category is topos. It has the same purpose as Heyting algebra for proposition. And of course, then you can construct examples based on this. What happens to topology? So you have opens always, and open is inside another open. Sometimes, say in algebraic geometry, and it really happened originally, the topos came from this intuition, that you have opens, and opens are kind of big, and you cannot localize really to see something, around something. And then you have to come up with more opens, and more opens work in a way that you need maps between opens, not just inclusion between opens. You have to address also maps. So say that I need some generalized topology here. Where you have opens and maps between opens, right? Not just inclusion. So there is also something in between, like this complete Heyting algebras. It's called Grothendieck topos. That I will explain what it is, but very roughly, it is just when you have all the limits also. All the limits or all the co-limits. That's not really true, but this is the general idea. No, with respect to sets, not just finite ones. All ones, but the diagram is a set. But there's more into it. It's not just that. But anyway, so these two are kind of the same. So I can use then the Grothendieck toposes when I define them as the new topology, and people do it in geometry really. And then in logic, this guy propositions with explicit proofs between them is called type theory. Therefore, this guy is just some sort of algebraic way to deal with type theories, some type theories, of course, right? And I guess that's it. So you can, whenever you want to think of a topos, think of it's just the soft Heyting algebra. It is Heyting algebra, but you have more morphisms than just inclusion, right? In a very coherent, good way. This is one way of thinking of it. So then any object in a topos can be an open set, right? So you say that I have a topos E, right? And then you have one object, like here, that you have this poset and you have one U, one object. You read U as open subset of the topological space. Here you can read X as the open subset of the space topos, right? Topos, the name comes from being a topological space that something happens, right? So this can be read as object, can be read as a set in a generalized manner, can be read as open in generalized space, can be read as a proposition in some sort of type theory or whatever, right? So you can read in different ways. We play with this later. So sorry to go beyond my time, please. Of course.
So, if you talk about the topology, so you only need like map between sets, or you add more higher object. Because I rather think that this should be something like groups. You need a higher order.
Not really. So I don't know what. Okay, so you are changing this to groupoids. You mean just the topological space to a groupoid?
Well, I need higher objects. I think they are called.
Yeah. Yes. Okay. Let's say something like this. If you want to generalize the notion of space, there are many ways. One way is to generalize the notion of topology, and this is what I'm talking about. It is kind of more general, more powerful. There's something else that is kind of perpendicular to this idea, that you can do both of them at the same time. And then you go from set-like objects to groupoid-like objects to higher groupoid-like objects, etc. Right? So you add more morphisms between everything. So in this sense, we are doing exactly the same idea when we go from algebra to topos, right? We are adding more morphisms. You can go from topos to say two topos, where you have objects, you have morphisms, and you have morphisms between morphisms, and so on. But the idea of generalized topology is kind of something else. Here you are changing the notion of really covering something based on something else, right? So
The reason I'm asking is that if you look at this picture, type theory. So in type theory, you have the hierarchy of type.
exactly.
And I don't see the hierarchy on the side of generalized topology.
True. So if you want to see the hierarchy, exactly, you have to go. Okay, so first of all, this type theory is kind of extensional type theory. So you need intensional type theory, and then you have levels. And when you have levels here, you also have levels. So this is a poset, then you have category, then you have two category, three category, and so on. Yes, keep going on also to the infinity. So to the infinity, this would be homotopy type theory, say, that would be just infinity categories. And also we have infinity toposes. So, right. Sure.
Is the generalized topology something I can Google, or what's the name? Like, what does this?
Of course, you have to search for Grothendieck topology. But the point is that this is kind of a vague notion that we want to formalize. And to formalize that, Grothendieck came up with the idea of Grothendieck topos. So that is really the formalization. So you have to know what is a Grothendieck topos. But there are ways to construct Grothendieck toposes that we will also cover here. So based on some generalized notion of topology, really, over a category rather than just some poset. And then there we can say that there is some sort of generalized topology where maps also important, not just inclusion. But we also cover that, I hope. Sure.
A non-trivial finite topos.
And non-trivial finite topos, no. Yeah, the whole thing is finite, you mean? Yes, no, I guess it is just one. Right. Because if because of the limits, yes, co-limits, yes, you can. Yeah, the point is that whenever you have just one and co-limits, but not the trivial one, You can have 2, 3, all the finite sets, so it explodes. Right. Okay, thank you.